have a pleasure to introduce Meelis Kull, who is Associate Professor of Machine Learning. In the previous life, he did PhD with me, not on machine learning topics, but more on bioinformatics. And he is a great example of what you can do during your postdoc. You can switch topics totally. And in the postdoc times, so Meelis converted into machine learning and has been contributing to the field quite a lot, especially on this calibration side. And let's hear what Meelis has to teach us.
Thank you, Jaak. Thanks for inviting me here. I'm local, but it's still great to be invited. I'm going to talk about uncertainty, which you already have heard quite a bit about from Eike Hüllermeier. But as he mentioned, he kind of left one piece mostly for me and only covered very briefly, and that was about calibration. So we are talking about uncertainty, and that's about machine learning methods that know how well they know, or know what they don't know, ideally. But we will have a particular setting in this. And now the animations don't work. Why is that? They worked earlier. Okay, next attempt. Now it does work. So, yes, we have heard quite a bit about uncertainty, but let me briefly come back to the fundamental question of why do we even care about uncertainty? I mean, intuitively, it's also, of course, a matter of trust, whether we believe that the machine learning model really knows what it is doing, and that's all important. But the important problem there is that machine learning models always make errors. We cannot make them perfect, and it's inevitable that they do make errors. And then that's where uncertainty needs to start to come in, because if we know how well it knows on a particular case, then we can potentially reduce the harm of those errors. How? For example, suppose we have an autonomous car, and if the perception system suddenly has high uncertainty about the current situation, then the car can start to slow down or brake even quite fast. Another example, from the medical domain, a doctor can run additional tests. For example, if the diagnostic tool that is based on machine learning is highly uncertain. So these are ways how, in a particular situation, knowing that there is high uncertainty can help us to reduce the harm of errors, and I think that's kind of the fundamental reason why we need to know about these levels of uncertainty. And I'm going to use two terms, uncertainty and confidence. They are highly related, but I'm also going to have technically making a difference between those two. And you will see soon in how I do it and how commonly in the literature it's done. So I already had examples about autonomous driving from the medical domain, but there are many other examples where uncertainty matters. In forecasting, we never know the future very well, and we need to know how well we know it in a particular case, because sometimes, I mean, for example, with weather forecasting, when it's kind of has been sunny for several days, it's all clear, we know it's very likely it will continue for a while. But then at some times where we know that the thunderstorm will arrive, but when exactly, that's quite uncertain quite often. Fraud detection, predicting client behavior, these are just some other examples of where we might care about uncertainty as well, because we could take some interventions, but these are always costly, and kind of knowing different levels of uncertainty is also important there. Right, I promised to say about how I use differently the terms confidence and uncertainty. And here's an example. So maybe it's about weather tomorrow. So maximum temperature tomorrow could be going above 30 or not, but maybe I'm 70% sure about it going above 30, and that's the way I express my confidence about a particular claim. So that's confidence. Uncertainty can be between two options, as in confidence, but it can also be between many more options. So, for example, the temperature could fall into different ranges: above 30, 25 to 30, below 25, with different probabilities. And these are mutually exclusive here, adding up to 100% of probability, 70 plus 20 plus 10. So uncertainty is about kind of a probability distribution across some possible events, typically mutually exclusive then, whereas confidence is about one particular claim. So typically, if a classifier is among many options, even if there are many options, if it only kind of chooses to provide a probability to the preferred option or to the predicted option and not any probabilities to the other ones, then that's confidence, whereas uncertainty is where we want to have the full probability distribution over all the options. Yes, so confidence attached to a predicted event, uncertainty, probability distribution over possible events. And I'll start with confidence and then later get to uncertainty also. Now, classifiers, we want to have them trustworthy, so we want to know about their uncertainty or confidence. Now, suppose a classifier has been trained. We have on a validation data set seen that it's 60% accurate. So what can we then say about confidence? In a way, we could say that on any future test instance, it's kind of 60% likely that we get the prediction correct. But that's true for kind of regardless of any instance, if we're then not making difference between different instances. And that's then a very weak statement. For any instance, it is 60%. What we want is actually to get instance-specific confidences. So for some cases, the model is more confident, but because the overall accuracy is still 60%, it cannot be higher, having higher confidence in all instances. So necessarily that means then that on some other instances, it is less confident. And confidence relates to class probabilities in a way that this is just, I mean, if the classifier reports class probabilities, one for each class, then the highest of those probabilities is going to be the confidence. And one way of defining trustworthy, well, in a limited sense, but is to require that the classifier is confidence calibrated. So what does that mean? So let's look at now all cases where the model, so all instances on which the model is 90% confident, 0.9. So that's kind of that bar that I'm going to look at. And now we are asking about, on that set, how accurate on average the model actually is. And what confidence calibrated means that out of all of those instances, it is indeed, on average, 90% accurate. That's kind of the correspondence of confidence to actual accuracy on that group of instances. So we are kind of conditioning now. So instead of looking at all instances, we're conditioning on instances on which the model is 90% accurate. And on that set, we are looking, so that's that argmax. So then on that set, we are looking at how often we are accurate. And accurate, we can now mathematically denote as y, which is the true class, equals the predicted class, which is the class for which we have the highest probability predicted. So that's the argmax p, p hat. And so what we want that to happen in 90% of the times that we are accurate. So that's the mathematical definition of being confidence calibrated. And I've kind of written it down for 0.9, but of course we then want to have this happening for any c between, in principle, 0 and 1. But we can't get very low confidences because we're always taking the maximum. So we cannot actually get confidence that are below 1 over the number of classes. Right, so now a particular example. So a data set CIFAR 10 of images, 10 classes, particular architecture. Overall accuracy is 94% of that model. But if we look at all instances with 90% confidence, well, in some range, around 90% actually, we need to, because the confidence is a real quantity, we always need to do some kind of intervals around these particular values. But actually in that range, it's only 58% accurate. And so it's clearly very overconfident. It is saying at 90, whereas actually it's only 58, so it's kind of very disappointing for us to find out, kind of suggesting we cannot trust the confidence levels that the model reports. And so there is kind of a big gap to what we would want it to be. So that red gap is now showing our not being calibrated. In this case, it's overconfidence. When we are under the diagonal would be the perfect calibration. Under that, we are overconfident in this right-hand side end. And we can then plot it over a whole data set and see that, in many cases, we are being overconfident, but not always. There are some exceptions here. But this plot also is, can be a bit noisy because it doesn't show how many instances actually fall into each of those ranges. So some ranges might have just a very few instances, and then the blue bar is also of very noisy height. And yes, as I said, at 94 overall accuracy, if we look at specifically one confidence level, 90% and around it, then it's 58% accurate only. ECE is expected calibration error, is a measure that kind of quantifies how far we are from the diagonal. Kind of averages the size of those red gaps. And it's a weighted average, weighted by the number of instances that fall into each of the bins. So yeah, here you see this number 0.0451, which is basically how far on average or how tall on average these red bars are. It looks a very low number, but it's low because actually most of the instances are in that highest bar near 1, and there the gap is small. So overconfidence happens often, But if you look at on the training set on which the model was actually trained, then models are typically calibrated. But of course, that's a kind of a sign of overfitting. And if you go to any other data, then it's not calibrated and it's overconfident typically. And for example, even if the test set is from the same distribution, so that's kind of our IID assumption, same distribution as the training set, then it typically happens that model is overconfident. But even more so on adversarial examples, as we just saw, or on out-of-distribution data that are coming from slightly different distributions. And now this is where we focus on a particular assumption. We are going to talk about test data from the same distribution as the training set during this talk. It doesn't mean that calibration couldn't be applied on other cases, but then you need also data from those other cases so that you can calibrate to those cases. So, but for now, let's just simplify things and assume there is no dataset shift, and it's just that the only thing that has caused this overconfidence is just our kind of learning algorithm potentially then overfitting to the training set. Right. So here was this example of a particular model being non-calibrated. Now, there is a well-known method called temperature scaling. And this is now the reliability diagram, as it's called, after we have applied temperature scaling. It's a calibration method. And now you can see that suddenly all the bars tend to be very close to the diagonal. So the predicted confidence level agrees quite nicely with the actual accuracy level. So in the particular example of this 90% confidence, we have now 88% actual accuracy in that group. That's nice. A question. Can we have a microphone, please? Or I can repeat the question.
So your measure is weighted by the...
Okay, there is a microphone. Thanks.
Your measure is weighted by how big the bins are, probably. So one way to make the measure 0 would be to put everybody at the same value, which is the overall accuracy, right? So do you also want to have the whole spread, or is that more like an automatic effect?
So what you just pointed out is that if you just wanted to get low calibration error, then that's something that you can relatively easily achieve. And so if if the model's overall accuracy is 94%, then what the model could do is to always predict 94% as the confidence level, regardless of what the instance is. And that means everything is in that same bin, and we are perfectly calibrated. Great. But that highlights that calibration is not the only thing that we want. We also want kind of a better discrimination between instances. And that's something, discrimination of confidence levels, and then proper losses such as log loss or cross entropy are measures that can capture that also. But indeed, so the EC measure is just looking at calibration only. So, if you actually give the same constant prediction to all instances, that of course means that you're also not predicting the right class. So you actually start to, then you can't be 94% accurate. So what you can do is just to always predict the majority class, if such exists, and then you collapse everything into a single bar. But if you, you don't know the classes perfectly, so you cannot just provide high confidence to everything unless you're a really good classifier. But yes, so the point is, EC alone is something that we shouldn't optimize for. We should always look at accuracy at the same time. Measures such as log loss are kind of combining the two. I'll get more to that. Was there another question? Not anymore. Yeah, okay. Right, so I mentioned temperature scaling, so let me get to explaining how temperature scaling works. So let's just look at any multi-class classifiers and implement this neural network, and let's not have calibration yet. Typically, we would have a softmax layer at the end, which then takes in logits. Logits are just any real values, which are then, there are as many logits as there are classes. Higher value of the logits suggests that the model thinks it's likely that it's that class. But then these real valued logits are transformed into probabilities through a softmax function, and then the probabilities nicely add up to 1. Now what temperature scaling is doing is putting something in between. So there is this, all the earlier part of the network, but then as you get to logits, then these logits will now be scaled with temperature scaling, dividing by a temperature parameter, and only then put through softmax to get probabilities. What it means, I mean, temperature is typically above 1, so you kind of make the logits closer to 0, and as an effect, because of the way softmax works, I'm not providing the formula here, but it's through exponentiation and then renormalization to ensure everything adds up to 1. By pulling the logits closer to 0, essentially it pulls the class probabilities closer to the uniform distribution and away from the extremes of 0 and 1 probability. Essentially that means you kind of pull down the confidence levels. If you do then fit this model on a separate holdout validation set, only optimizing for this temperature parameter, keeping everything else frozen, or the rest of the network is still the same, then that's how you do temperature scaling. Find out the good value of temperature parameter, essentially finding out how overconfident your model was, and now starting to correct for that, and that's what you would now, from now on, do on all the test instances. Apply this temperature. And this temperature is optimized with same way, typically cross entropy, as the rest of the network. It's just that now the rest of the network is frozen, and now it's not the original training set, but it's a holdout validation set, sometimes called also the calibration set on which we do it. Right, and so if the original plot was like this for the reliability diagram, suddenly now, nicely, we have almost calibrated probabilities in this confidence reliability diagram. However, we could look at different kinds of reliabilities as well. So here I have looked at only probability for class 2. So it's 10 classes task. So we're now looking at probability predicted by the model, by the same model, to class 2. And we are looking at comparing that, how frequent actually class 2 is in those different probability ranges. And yeah, for example, taking again probabilities near 0.9, we see that the actual frequency is less than 80%. It's actually 76%, which is quite far from that promised 90%. So even though the model was confidence calibrated pretty nicely, it's not calibrated in class 2. And so after noticing that, we developed a method which we call Dirichlet calibration. And once you apply that, you tend to get also pretty well calibrated probabilities for each class separately. How that works. So this was, before I get to this Dirichlet calibration itself, I'll show you some variants of temperature scaling that the original paper that proposed it also considered. So this was temperature scaling, as I explained, but the same paper also considered vector scaling. So in temperature scaling, you have this division by the same temperature. So it's a kind of a very particular linear operator that is applied. But now in vector scaling, you actually fit a linear function on separately on each of the logits. So there is a weight and bias, a different one potentially for each class. And then otherwise all the same. So that allows kind of class-specific adjustments to well, confidence, you could say, but it's to the logits really. They later turn to probabilities, and from them the highest probability is the confidence. And there is matrix scaling, which is doing even more. It's I mean, in vector scaling, now I went too far. In vector scaling, you put in the same logit here and transform it, whereas in matrix scaling, you actually give information. I haven't drawn all the arrows, but all the other logits also can contribute to how we transform this particular logit. So it's a fully connected layer, you could say. But otherwise still linear transformation. So a matrix that we multiply. So it's matrix multiplication here, and bias vector added. Right, but the original paper said, well, unfortunately, this didn't work well. So we found a way to make it work. But let me now explain how Dirichlet calibration is different. Is that, I mean, matrix scaling and all this vector scaling, temperature scaling, all need this neural network, all needs these logits, and then you can apply it. Whereas for Dirichlet calibration, we have developed it in a way that it works for any probabilistic multi-class classifiers. Doesn't need to be a neural net at all. Can be anything classical, support vector machines, k-nearest neighbors, whatever. About the name, there were existing binary classification methods, Platt scaling, that also works in the logit space, although originally developed for support vector machines. And then beta calibration that we developed earlier, which works in class probabilities. And then it is kind of possible to derive these from distribution assumptions, Platt scaling from Gaussian, beta from beta, and then we just generalized to multi-class, and that's how, because the generalization of the beta distribution is a Dirichlet distribution, then that's how we got to the name. And there is, but then matrix scaling is then kind of the equivalent for logit space. So how Dirichlet calibration works is that we first transform the probabilities through the logarithmic transform and kind of get back to logits. These are not the same logits. It's kind of, we could call them pseudo logits, and then apply basically matrix scaling. Looks a bit ad hoc. Why log transform? Why in this particular way? But it's kind of has a principled derivation. If we would assume that for each class separately, the predictions form a Dirichlet calibration, Dirichlet distribution, then from that assumption you can actually prove that then the optimal calibration transformation would have this kind of a form. But then we can optimize this just using cross entropy as with any other neural architecture. Importantly, we showed that this there is important to do regularization, otherwise it can overfit very badly, and that's why the earlier paper said this matrix scaling doesn't work, because I mean here we also have this matrix multiplication, so matrix scaling, many parameters on a relatively small data set. It typically badly overfits, and what we want is then to push down all the kind of off-diagonal entries in the matrix, which means that it's mostly the same probability that affects the calibrated probability for the same class, and the others, the effect of others should be there, at least for some classes, but we should push them down a bit, otherwise we overfit. Just briefly to show, I mean, any new method needs to come with experimentation showing that it is really outperforming earlier methods. So we had non-neural experiments on things other than neural nets, classical classifiers over many data sets, and particularly also highlighting a bit that, I mean, it's not only, well, we're in these experiments to train test splits or actually cross-validation, but then we also need to separate the calibration set from the training set. So it's so the calibration set shouldn't be the same as the training set, because otherwise we see that we are quite well calibrated on the training set, but actually we don't see new data, and that's an overfitting issue. Right, and then looking at critical difference diagrams, which is then kind of averaged ranks over many data sets, typical way to visualize these kind of differences. The only reason I'm showing it is just to emphasize that one needs to look at not only EC, but also the error rate and log loss, because as was mentioned, EC, you can get a good EC near zero, even if you just have a constant classifier that always predicts the same confidence, same class probabilities for everything, and that's a bad thing to do.
Meelis, sorry?
Yes?
Maybe I missed it, but in order to choose and train this, you need a criterion of what is a good calibrated classifier, right? So what exactly was the training objective or the selection objective?
So the training objective is cross-entropy, simply. And the reason why it works well in kind of getting well-calibrated probabilities is that it's a proper loss, and proper losses incentivize the model to output uncertainties in a calibrated way.
But the original data would also have been trained with cross-entropy, right?
Yes.
So, and your statement was it works on the training set, but it will not work on new data then?
Yes, because why it works, let me maybe go to, yeah, I mean the original, okay, maybe let me go to just to the simple example of temperature scaling. So the thing is that this original feed-forward network training gets overconfident on the training set. Now, why, and it's trained with cross-entropy, why is it now not getting overconfident if we also optimize cross-entropy on this calibration set? The reason is that now we are fitting only a single parameter, the temperature. So it's so restrictive kind of parametric assumption that it just cannot overfit anymore. Or, well, always overfits, but just so by so tiny amount that it doesn't matter anymore. And the same is then true for the following methods. It's just the kind of capacity limitations that don't allow the model to overfit on those calibration data. They still do if the calibration data set is maybe too small compared to how many parameters we are, if we don't apply regularization enough, but that's the key. The capacity needs to be, the complexity of the calibration model needs to be heavily restricted. Just for fun, we looked at which classical classifiers tend to be more often calibrated. There is a kind of statistical test for calibration, so these proportions here are actually how often the model is not significantly non-calibrated, because that's how we can do the statistical test. So naive Bayes is the worst in calibration because it's kind of double counting the evidence and just naively assuming independence, conditional independence. Random forest somewhere relatively better, but it's just on that particular data set, or set of data sets. Sorry. Yeah, and once we have calibrated, then Dirichlet calibration tends to be more often well calibrated. But even calibration methods, well, they are just limited to their data sets that they are applied on. Also, the parametric assumptions can not be good, so we might not achieve very, very well calibrated or near perfect calibrated probabilities either. And this is also experiments on neural architecture, on different data sets, different architectures. Yeah. Maybe one just point I wanted to make here is that some of the differences in numbers can be quite small. I mean, just taking a CIFAR10 ConvNet, class-wise EC, and different calibration methods, and the numbers are, well, 4, 4, 4, 3, 4, 5. So this EC differences can be quite small sometimes. This is where temperature scaling, for example, does a pretty good job already. So maybe there is not even a need to go into anything more complicated, whereas some other cases, it's no longer true. Right. I wanted to also get back to the fundamentals about kind of how calibration works, and then going to the simple case of binary classification, because for now I just showed some architecture images, and maybe that doesn't convey necessarily how what the kind of the challenges are in calibration. And so here is a very, very small example from binary classification. So we want to predict positive or negative, and more particularly want to have a score, or ideally probability. So probability 1 means confidently class 1, probability 0 means surely not class 1, so that means confidently class 0, or negative class. And the ground truth that we get from the calibration dataset is just whether it was actually class 1 or actually class 0, but we don't get the probabilities. We never see what the true probability should have been. And still, we need to be able to learn how to predict these calibrated probabilities. So it's a kind of odd kind of a regression task. We want to get real numbers as outputs, but our target labels that we observe are still zeros and ones. So kind of classification in terms of labels, but regression in terms of the target that we want to predict. But practically, it is actually, you can treat it as regression. And it's typically, you assume that it's a monotonic transformation. So higher probability should also, so higher predicted probability should transform to higher calibrated probability. And so it's a monotonicity assumption. And then you can do stuff like isotonic calibration, which minimizes the squared error under the assumption that the curve needs to be monotonic on this particular training set. And you get something like this, so with linear interpolation in between. And actually, it's equivalent to maximizing the likelihood on the training data. There are several existing binary classification methods. So logistic calibration or Platt scaling is just fitting a logistic function. Isotonic I mentioned. We had this beta calibration from the beta distribution assumptions derived a family. Sometimes you can consider violations to this monotonicity, so that's the near isotonic calibration. But I'm not going into details there. Something that you might consider is also the bias and variance aspects. So here in these figures, what we've done is to look at many different training sets for these calibration models. So essentially calibration sets, many copies, I think 10 sets, so 10 blue lines are what are being learned, whereas the red dashed line is the ground truth. So it's a synthetic case. We know what the true calibration map should be. And yes, with strong parametric assumptions like logistic function or this beta calibration map family function, you're not able to fit that curve because that curve does not belong to your family that you're fitting. But at the same time, at least you're stable. You almost always even, different training sets tend to give almost the same model. Whereas if you do isotonic, which is bottom left, you have much more noisier case. And then we had also a Bayesian version proposed, which with Meelis Kull, which worked in a more stable manner. Right, but now that was just briefly to list some methods from binary calibration, but now to multi-class. And I mentioned the terms class-wise calibrated and confidence calibrated, but there is also a stronger notion. So that's in the middle there, that's multi-class calibrated or distribution calibrated, and that's where you assume that conditioning on the whole vector. So if you take all instances for which the prediction vector is almost identical, so not only for looking at one probability in that vector, but all particular configuration of those probabilities, and then among all those instances, the actual class distribution needs to agree with that. That's a very strong notion, which one might also consider aiming for. Probability simplex is something that you saw in Eicher-Hüllermeyer's talk as well, but so here it's again. So this is a way to be able to talk about three classes in a visual way. So class probabilities across three classes. So every point in this triangle corresponds to one particular class probability vector. There is a guarantee that for any of those points, the three probabilities for the three classes indeed add up to 1. So that's kind of cutting the 3D space with a plane which ensures that the sum of 3 dimensions is 1. So in the corners, you have kind of full confidence for that particular class, so probability 1 and 0 for the other. And then in the middle, you have the point where you're the most uncertain, where you have 1/3 probability for each of the classes. And now we get to look at a synthetic task, just for visualization, where the model is not calibrated, and the arrows here mark the perfect calibration transformation or calibration map. So whenever you have some prediction from the model, then what you need to do is to let's say it's somewhere here is the, well, somewhere here is the actual prediction, and then you follow the arrow to see how you should transform that prediction to get a perfectly calibrated classifier. Now, in the strongest sense, in the sense of distribution calibration or multi-class calibration. But you could also instead, so this allows you to kind of look at this distribution calibration, but you could compare that to, okay, I just wanted to highlight there's that one point where you already are calibrated, the arrow is almost zero length. But you could compare that to the ways we visualized earlier with the reliability diagrams. So, but now I'm showing the reliability diagram with this odd way where the bars have these tilted tops. This is something that we came up with recently with Markus Kängsepp and Kaspar Valk. In that bigger paper, with this one small thing is that instead of showing the bars in the standard way, we turn them 45 degrees, because that actually allows visually to estimate EC, because now EC is actually the average difference from the diagonal instance-wise. Skipping a bit of detail here. But visually, we can now see it more like a line rather than this staircase, and so it's easy to see calibration errors. Now, the middle or the left plot has this overall three class vectors, and whereas the right-hand side only shows one class, so that's actually for class 0, the right-hand side plot. So the correspondence is that where you have class 0 having very small value, 0 to 0.1, that's this box. And on the right-hand side plot, that's visualized here. So right-hand side plot kind of aggregates this whole region on the left into a single bar. So it's clearly aggregating more information. So that's the correspondence between those two. And if you do temperature scaling that I showed you earlier, then visually, all it does, it pulls everything towards the uniform distribution in the middle, lowers the confidence. And yes, if you apply it in this particular case, then it is doing quite well. The arrows are now much shorter, so it means we are less far away from being perfectly calibrated. The gaps on the right-hand side are also shorter. Whereas if we apply Dirichlet calibration, we are doing even better. Now the arrows are even shorter, everything even closer to the diagonals. It's just a visual way to confirm that we're doing a good thing. Now I'll briefly talk about a very recent paper by a Stanford group published at NeurIPS last year. And it's relating calibration to decision making. I mean, these relationships were established before, but they are building on it. And what they do is, I mean, eventually we have probabilities as a way to quantify uncertainty. Eventually, someone needs to do some actions based on that. That's why we were looking at, that's why we wanted to get predictions, we wanted to get uncertainty. Eventually, we're getting to some decisions or actions, we could call them. And then, typical way of trying to optimize behavior is to kind of reduce the overall loss of actions resulting from actions, or cost resulting from actions. So we could look at loss functions or cost functions. that for each pair of actual class, which is this y, and our action, which is a, results in some cost or loss. I mean, as an example, we might have maybe it's X-ray imaging, and we have different potential diagnoses that we could put, and these are, or maybe not diagnosis, but maybe actual states or diseases. And now we can make decisions. Eventually, we need to make decisions whether to treat or not to treat. And then, depending on what the actual condition was, the loss that we have as a result of treating or not treating might be different. And that's kind of reflected by the colors in this matrix. And in principle, we could just look at arbitrary action sets of arbitrary sizes. Typically, this paper fixes to one particular number of actions. For a particular set of actions, we can, and a particular situation, having an uncertainty quantified by predicted vector p hat x over the classes, what we might want to do is to minimize the expected cost from our action. So we consider all possible actions and find the one for which the expected cost is going to be the smallest, assuming that our uncertainty is well calibrated. So, and it's called Bayes decision function in this case. And we could consider many different such cost scenarios or loss scenarios, matrices. And for each of them, there exists a kind of right way of making decisions, the Bayes decision function. And now what the paper defined was decision calibration, which is another now definition of being calibrated, but it's weaker than, or typically is weaker than distribution calibrated. So instead of requiring that all the probability vectors are calibrated, we require that our actions that we take, if we take them optimally, are not affected by us being not maybe perfectly predicting everything, or not perfectly being not perfectly calibrated. So essentially, what the requirement here says is that assuming, so we have a predictive model p hat, and then the decisions that we make, so all the estimated losses we estimate based on this uncertainty are actually in agreement to kind of with respect to the case where we would be perfectly quantifying our uncertainty. So if the data, so if the data is drawn from our estimated uncertainty, so the class labels are drawn from there, compared to if they were drawn from the true generating process, our estimates of loss don't get affected. So kind of quite, in a way, complicated definition, but very powerful one. And what then they showed is that then looking at different sets of actions, you can relate this decision calibration notion to many other existing calibration notions. In particular, if you look at all your class labels plus some kind of abstain label, so or reject label. So the kind of the possible actions are either we predict one of the classes, or we say we abstain, or we decide not to make a prediction. And then for that, there is a lower cost beta than the full error cost. Then under that model, requiring decision calibration in the sense of the previous definition, actually is equivalent to requiring confidence calibration. And then you could have another set of actions, which is then for any particular class. You could either say it's yes, it's that class, or not, it's not that class, or I abstain, and that gives you class-wise calibration. Or you could consider all possible sets of actions, and then that corresponds to the same most strong notion of distribution calibration. So that's what they kind of came up with a new notion or set of notions of decision calibration. But then they could also make it practical in terms of coming up with a method. So once you decide a certain number of actions with a finite set, a fixed number, they tried, I think, 5 or 2 actions, then if you have that, then first of all, the decision boundaries between your different actions are going to be linear. It turns out, I won't go into detail, but it can be seen relatively easily. And what they then do is to define an algorithm that I think, so first of all, this will have now guarantees that in the limit of infinite data, you get perfectly calibrated probabilities, and nice thing to have. And so it has consistency. But let me explain it through an example. So what they do, the same example that we have. By the way, I forgot to say what the colors denote. The colors are just redundant in the sense that they are according to the arrow encoded. So arrows that go in the direction of class 2, no, class 1 are green, or against the class 1 direction. So class 1 is this corner. All the arrows that go away from that corner are green. All the arrows that go away from top corner are blue, and so on. And so all the mixtures of those colors. Just to see better in how, I mean, we can't draw arrows everywhere, but colors we can draw everywhere. But now what this algorithm does is trying to find among all possible sets of actions of a particular size, so all possible loss matrices, find the one which is the worst for this classifier. So what it practically means in case of 2 possible actions is that it tries to find the linear boundary so that the model, on average, both sides would be kind of as far from being calibrated as possible if you kind of average the sizes of arrows. So on this kind of below this brown line here, all the arrows tend to be on average going in a bit kind of upwards, quite a bit, and in that top blue part tend to go downwards. So then this method applies just a constant transformation on both sides. Very simple. So almost a trivial transformation. But then it continues. So reliability diagram now after this first iteration is this. So arrows tend to be already a bit smaller. But now it continues, again finding the worst possible case and then improving it. And continues in this way. And after 9 iterations, you get something like this. And if you look at the reliability diagram, the arrows are going to be already very small. And yeah, they have guarantees in the limit of infinite data, you get perfect calibration. By the way, it's just a kind of sequence of very simple models. Every next is aiming to fix the errors of the previous one. Does that remind anything in the machine learning classical methods? Any particular methods that does sequence of simple models, every next tries to fix the early errors? Okay. Yay! Boosting, that is. So that's boosting. It's actually slightly different here because boosting is additive, but this is composing functions, transformations. But with Kaspar-Valk, we checked that if you would implement it in the boosting way, just by adding transformation, that would also work. Right. But you could push the number of possible actions to more. It could be 5, for example. But what tends to happen is also that despite the guarantees, so the theoretical guarantees are always nice. In practice, this will overfit. On finite sets, it overfits. And so you need to do early stopping of this. You can't do too many steps. Right. What you can also see is that, I mean, after iteration 9, you can kind of still see quite sharply the first split that you made, or first and second splits. So, and due to that, well, it isn't doing too well. I mean, it's quite well, but not too well. What you can do, though, is to do the same on top of temperature scaling, because temperature scaling already gives you quite well calibrated probabilities, and then you do this on top. And then you're doing better. Now, something that we then looked into was that, do we really need these kind of relatively complicated methods? Can we do something very, very simple? So with Kaspar-Valk, we looked at, can we just do KNN? And it turned out it works well. So boosting worked well, but KNN can work even better. It's the tiny difference in how you apply this KNN is that instead of looking at average label in your neighborhood, what you need to do is to look at the average deviation or average difference of your prediction from the one hot label, and to KNN averaging based on that instead, because typically in the neighborhood, the perfectly calibrated predictions are not as similar as the differences between your prediction and the perfectly calibrated prediction. Right, and then our method on top of temperature scaling is also then even better. Now, starting to wrap up, I mentioned that because of overfitting, we want to restrict the complexity of the model in calibration quite a bit. And one way of doing that is parametric. But then we see also non-parametric methods are still useful, but then in the last method that I showed was a combination of temperature scaling, which is a parametric method with a single parameter, and on top of it KNN, which is non-parametric. But then just, is there a better way of doing that than just one after another? Also, all that I was talking about today was concentrating on the situation where train and test are from the same distribution. If that isn't the case, if there's out of distribution issues, if there's adversarial examples, all that is a separate story. So getting any guarantees that your models are calibrated even then is, well, it's open research question, not existing yet. Maybe under very strong sets of assumptions you can get something. And then I talked about classification, but then you could also consider regression. Their uncertainty means that instead of predicting or outputting only a single real value, as you typically do in regression, you also want to have a distribution around that value. Could be a Gaussian, could be anything else. Or structured prediction, where you have more outputs, and then maybe they need to have some structure, and maybe you want to predict text. How can you then produce uncertainty around the predicted text? Think of translation. You produce the translation model produces a sentence, but can it attach confidence? Can it attach more information than just that confidence? Maybe saying that, okay, maybe there's overall confidence, but maybe on these particular words I'm less certain. Maybe I even give a set of alternatives for a particular word and the probability distribution over them. So there are ways you could try to get uncertainty in more complicated situations. A lot of work to do there. So to summarize, calibrate, the goal of why we are even looking into uncertainty is that allows us to reduce the harm of errors. Overconfidence is very common on same distribution even, but of course in adversarial examples and outer distribution. I've told you about many methods, many notions of how we could even define what we mean by being calibrated. And even if some method offers you guarantees, these might be asymptotic, and you might, on finite sets, still observe overfitting, and so you need to be a bit skeptical of the guarantees. You need to carefully look at the assumptions. And then sometimes very simple methods can work well. Thanks very much. Questions?
Please calibrate your questions.
Question, would you relate this calibration maps and robustness? And then if yes, then how? Because it seems that when the surface is very wrinkled, I would kind of hypothesize that there might be certain problem with robustness in this area.
Mm-hmm. So we've seen, robustness itself, typically maybe as a term starts to require robustness against maybe adversarial examples, against auto distribution case, whereas I was mostly talking about same distribution. On the same distribution, it's a bit easier, I would say, because our testing is done on the same kind of generative process as we want, as the overall test population. So we want to, well, it's not biased. Our testing is not biased. So as long as kind of our average performance seems good, it kind of could be called maybe robust, except that maybe you want to look at the worst case performance as well. So maybe in most cases, on average, it's nicely calibrated, but there exists some odd cases where it is far from it. Maybe your test set size is not sufficiently big that you necessarily capture that, but on average, you would. smoothness is still a nice thing to have. So developing calibration methods, we try to enforce also some smoothness, but yeah, extensive test set will recover that in the case where it is from the same distribution. But of course, that doesn't work on adversarial examples out of distribution.
Thank you for a nice talk. If I understood correctly, in the Dirichlet calibration, it used quite a powerful transformation, and there was a chance that it could overfit. And I was wondering if you tried using some less powerful versions as well. So, for example, you could use just a different temperature for each logit, something like that.
Yes. Getting there.
Yes.
So, Dirichlet calibration itself was this, and yes, it could overfit because there is quite a lot of capacity here, many parameters. The number of classes squared plus the number of classes, and that can overfit. We defended against this with regularization, but your question is whether we can just basically reduce the number of parameters itself. And indeed, yes, you can. You could basically do the same thing as this vector scaling was, where you have as many parameters as classes twice, k plus k. And you could even have, you could even go back to temperature scaling, which actually turns out to not care whether you went through these logits and then pseudo logits like temperature scaling doesn't care whether you go through taking log transform and then again softmax. Although it's a lossy transformation, loses 1 degree of freedom, but even then the temperature scaling is invariant. But for vector scaling it does matter. So whether you apply it directly on logits or if you go through softmax and then take log transform. So all that I wanted to say with that is if logits are available, then it's preferable to use the original logits and not to go through this softmax and then back log transform going to pseudo logits, because you lose 1 degree of freedom.
Okay, are we done? No questions? PhD students who have contributed did not jump out and say that you did not understand anything what I did. Thank you, Meelis.